Well, my dear participant, now I am going to talk about Box-Jenkins methods. Box-Jenkins, these are the two great authors. George Box was son-in-law of Sir Ronald Fisher, the father of statistics, and he was a great statistician. He has contributed many things in terms of quality control, in terms of time series. His book on time series came in 70s, and that is a remarkable, and they gave the concept of Box-Jenkins method. So what Box-Jenkins method involves? The following step: model form selection, evaluate stationarity, selection of the differencing level D to fix stationarity problems, selection of AR1 model P, selection of MA model Q, level Q. So these are the Box-Jenkins, parameter estimation and model checking. So these 4 steps constitutes of Box-Jenkins methods. Stationarity. A stationary time series is one whose statistical properties do not depend on the time at which the series is observed. The standard algorithm for ARIMA models assume stationarity. So it is important to check the stationarity of the time series. Stationarity means it should behave like white noise. The two widely used tests for stationarity are augmented Dickey-Fuller test, ADF dot test, which is in which H naught is series is non-stationary, whereas KPS test series is stationary, H naught. So here these are the two contradicting. H naught for ADF test series is non-stationary, whereas for KPS test H naught series is stationary, and these two are from the package T series. So test on CO2 data, library T series, and then CO2 data. I think I have already talked about CO2, help CO2, it is in the package data sets, manual low atmospheric CO2 concentration. We have already discussed this data. So now I am going to talk about an example on this. So library T series, because we need to install T series package, and then library T series, and then ADF dot test CO2, using ADF dot test, because this function ADF dot test is available with the package T series. So that's why we have to require our library T series, and then we have to use ADF dot test. Augmented Dickey-Fuller test. Dickey-Fuller test statistic is this: lag order is equal to 7, p value 0.2269. Alternative hypothesis is stationary. Here the null hypothesis is non-stationary, alternative is stationary. And reverse of this is with the ADF test. From ABF test, the p value is 0.2, which is actually here it should be not less than, which is not less than, it is a correction is required, which is not less than the usual level of significance, which indicates that we will fail to reject the null hypothesis. KPSS dot test, here p value is 0.0 and here 0.0, the p value associated with KPSS test 0.0. This means that the null hypothesis of stationarity is rejected. The null hypothesis of stationarity is rejected, because in KPS test the null hypothesis is that series is stationary, and that has been rejected because of p value is less than 0.05. Hence the time series is non-stationary. So both the tests are giving the same result. both the tests are giving the same result. So, stationarity we have already discussed, and these are the two tests, ADF test, and we have got the result. Now, dealing with non-stationarity, how to deal. This is the main feature of Box-Jenkins method. How to deal, because for fitting an ARIMA model, it is must that series should be stationary. Stationarity is required at many places, like in Markov chain Monte Carlo, in Bayesian data analysis. We need that this series must be stationary. So, dealing with non-stationary, if the time series fails the stationarity test, then the approach is Box-Jenkins method, is that the differencing to make the time series stationary. In R, we have the function diff in base, which have the following components: x, the data, lag, the lag at which the difference, and difference order of the differencing. The difference of 1 removes linear trend, whereas the difference of 2 removes the quadratic, and difference at lag equals the frequency, remove the seasonality. So, CO2 diff is equal to x is equal to CO2, this is a time series, lag is equal to 1, differencing of 1. So, ADF test, here it has been rejected. So, the series is non-stationary, has been rejected by the ADF test. So, that means after differencing CO2 diff, the first differencing, the series becomes stationary. And same thing we will get through KPSS test. Here p value is 0.1, and that means here stationarity is H0, and that is being accepted. Plot.ts, see, this is the plot of the differencing, which looks like white noise. And that shows that series is stationary. And after a differencing of order 1, we see that CO2 data pass the stationarity and becomes a stationary time series. So, we will run these commands. First, we will make the differences, and then we are getting the plot also of differences. So, this thing we have. Now, fitting and estimating parameters. Fitting and estimating parameters. Suppose we want to fit and estimate parameters ARIMA model on simulated data. So, here simulate AR2 with a drift m is equal to 5. So, ARIMA.sim, n is equal to 1000, model list AR, the coefficient of AR 0.8, 0.1 plus m. So, library forecast ARIMA, capital ARIMA, ARIMA is a function of forecast package, whereas with the small letters ARIMA, it is a function of base R. It is a function of stat package in R. That is in the base R. But here you have to install forecast and then you can call this ARIMA. AR2, this is the simulated data, order C20, 0, include constant is equal to true, because we want this constant to be included. So this is the AR1 0.77, here 0.8, so they are very close. This one is 0.1, so it is 0.09, and mean is 5, so because include constant is equal to true, so 5.2, and these are the standard errors. And sigma is 0.99, because we have not specified here in the simulation sigma, so that means sigma is 1, by default it is 1, so sigma square is equal to 0.99, and log likelihood is minus 1415.441, AIC, AICC and BIC. These are the criterion for model selection. We can see that the estimated parameters are very close to the true parameter values. Simulate data simulation from ARIMA 1, 2. Here it was ARIMA 2. Here it is ARMA 1, 2. So here AR is of order 1, whereas MA is of order 2. MA is of order 2. So now ARIMA 1, 2, ARIMA.sim, n is equal to 100, order list AR is equal to C 0.8 and MA 0.8 and 0.2 plus M, mean forecast ARIMA include. So these are the coefficients, AR1 0.5, 0.58, and here it has been specified as 0.8, but here it comes out 0.58, and MA 0.8, so it is 1.12, and 0.2 it is 0.6, and this is the mean. So we can go to the data and we can run them, because of our number of observations is less here, that's why we are not getting the true results. If we will make it 1000, see what will happen. If we will make the number of observation 1000, see what will happen. Like here it is 1000, so it is matching. It is matching. So here 0.77, 0.09, and here now it should match the results. See here now 0.8, 0.8, MA 0.8, it is also 0.8, so 0.2, 0.2. So if you will have number of simulation less here like 100, it is not recommended. It is not recommended. At least you should have 1000 observations to conclude to the results, to the good results. So you should keep, see here it is differencing, whereas with 1000 it is giving good results. It is giving good results. So these things 83, 0.8, 0.7, 5, that is 0.8, and 0.2, 0.18. So this way it is. Now auto.arima, see the forecast package has developed, it has a function auto.arima. The package forecast by Heidman et al. 2024 in R contains the function auto.arima that returns ARIMA model according to either AIC or AICC or BIC values. So ARIMA, auto-ARIMA, actually what it does, it makes the data stationary, it goes for differencing and they made the data. Then it chooses the order of the model also. What should be the order of AR1, what should be the AR, and what should be the what should be the order of MA. So all these things are done in auto.arima, and that's why auto.arima is very popular. We are going to have Nile's data, Nile. I would like to show you Nile data. Help Nile. Nile, Nile. See, Nile, it is in the package data sets, flow of river Nile, measurements of the annual flow of the river Nile at Aswan, formerly Aswan, 1871 to 1970 in 10 raised power 8 m raised power 3 with apparent changing point near 1898. Cobb 1978 table 1 page 249. So format Nile, source it is Durban, Koopman, time series analysis by state process, and these are the data of Nile. So Nile is a time series object. If you see the str of Nile, it is a time series object. It is a time series object, and it has a length of 100. So we are going to discuss now not simulated data, a real data, and we are going to fit this ARIMA library forecast plot.ts Nile. So this is the time series plot of the Nile. See, it shows that with the change of time, with the increasing time, there is some decreasing trend in the flow level. There is decreasing trend in the flow level. This is the 1898. M is equal to auto.arima Nile, and see what model it suggests. It suggests ARIMA 1, 1, 1. So that is, it is of order AR1, MA1, and with single differencing. And these are the AR1, MA estimates, standard errors, and these are the sigma square, and these are the AIC 1267.25. The auto.arima function automatically fitted an ARIMA 1, 1, 1 model. That means it is the best model based on AIC and BIC for the data. Now, I am going to talk about forecasting. For every model, you need a forecast, because the first thing is that construction of a model, and then estimation of parameter, that is known as model fitting, and then ultimate goal is forecasting on the basis of that model that is required. So here I am going to talk about forecasting. The function forecast is used for predicting the future values. F is equal to forecast M. M is the fitted object. M is equal to auto.arima Nile. And here this stands for span of forecasting. So it is 1970s up to data is given, and now we want up to 12 years forecast. So 1971 to 1982, 71, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 year forecast. So this is the point estimate of the forecast, level of the flow. This is the low 80%, high 80%, low 95% confidence interval and high 95% confidence interval. So the argument H indicates the length of future period for which prediction is needed, and plot C, plot F forecast. So this is the model. These are the observed values and these are the forecasted values. These are the forecasted values. So, and this is 80% forecasted values and this is the interval of 95%. 95%. So, now we can go to the library forecast. Then this is the time series data of Nile, and then we are going to use library forecast plot.ts, then m is equal to auto.arima. So this is the fitted object m, this is the fitted object. It is arima 1, 1, 1. So that means it chooses order that is AR1, MA1 and with single differencing. 1 stands for single differencing. And these are the estimates of AR1, MA1 and these are the standard errors and these are the AIC. Actually, if we will have any other value of these AR1, AR2, that will be greater than this AIC. So it provides the least AIC value. So on the basis of AIC value, we are selecting the model. And this is the time series plot. Then forecast the auto.arima function automatically fitted an ARIMA. This model, that means that it is the best model based on AIC and BIC from the data. Akai information criteria or BIC. Minimum AIC is the best or minimum BIC is the best. Forecasting, the function forecast is used for predicting the future. It is available with the C, help forecast. C, forecasting from the object gen series and number 1 is forecast. So we will click on forecast. So forecasting function linear models and help pack is equal to forecast, and here function name is also forecast. So function name is also forecast. Forecast TS. Yes, forecasting time series data. See description, forecast is a generic function for forecasting from a time series date models. The function invokes particular method which depend on the class of the first argument. Actually, we have already got the through auto.arima. We have already selected a model, and on the basis of that model, we are going to forecast. So these are the help of the forecast. So here Up to 1970 data is there, up to 1970 data is there. So now 12-year forecast we want, so that's why H is equal to 12. So 1971 to 1982, I think 82 or 83, it is view F yes. No, it is not giving the, here it is not working. Yes. So here it is giving up to 12, 1 is to 12. So there are 12, 80, then 81, 82, 83. And these things we have already seen in the PDF. See here, up to 12 year, 1982, 1971 to 1982. So, and plot forecast, plot F, give this plot. So, these are the observed time series data and these are the forecasted data. This is the 80% interval and this is the 95% confidence interval of the forecasted values. Now, in my next lecture, I shall be talking about analysis with FPP2, forecasting principles and practice by Rob Heidman and George Athenopoulos. It is a great book nowadays in time series and forecasting. So, I would like to cover from that book only now.